Imagine for a second that you have a personal assistant. And I don't mean a typical assistant. I mean someone truly incredible. Like they
Right.
read every single book you own, every article you bookmark, every document on your desktop, and they just organize it perfectly.
A literal super assistant.
Exactly. You ask a question and they instantly pull the exact right folder. But, well, over time, as you keep tossing them new documents and asking them increasingly complicated things, their filing system starts getting messy.
Oh, yeah. The inevitable chaos.
Yeah, right. They start losing the connections between ideas. They duplicate files without realizing it. And worse, they start hallucinating facts because they just can't find the original source material anymore. Now, how do you fix their memory without making them, sit down and reread your entire library from scratch?
I mean, it sounds like a massive headache.
Yeah.
And it actually is a massive problem in computer science right now. It's exactly the issue we are tackling today.
Welcome to today's deep dive. We are looking at a state-of-the-art generative AI paper that introduces a groundbreaking solution to this precise problem. And the system they've built is called DeepRefine.
Yeah, and if you have ever relied on an AI to remember complex information or manage a massive project or just act as a second brain, the mechanics of how this works are going to be incredibly relevant to you.
Okay, let's unpack this. What exactly is the core problem the paper is addressing? Because before we can understand the fix, I feel like we really need to understand the architecture of the AI's memory first.
That's honestly the best place to start. We need to set the stage with something called agent-compiled knowledge bases, which are built using RAG.
Right, and RAG stands for Retrieval Augmented Generation, for those who might not know.
Exactly. Normally, an AI model is limited to whatever data it was initially trained on. So, like, if it was trained in 2023, it doesn't know what happened in 2024.
Because it's locked in time.
Right. But RAG changes that rule by allowing the AI to essentially reach out and pull information from an external database to answer your questions in real time.
It's essentially giving the AI an open book test instead of a closed book test. It can literally just go look up the answers.
That is a perfect way to put it. But the most advanced versions of these systems, they don't just dump raw text into a giant digital folder. They compile all those documents into graph-structured knowledge bases.
A graph structure, like a chart.
Think of something like a massive, interconnected Wikipedia, but it's run entirely by the language model. The AI ingests the sources, synthesizes the information, and organizes it into a giant web of nodes and edges.
Okay, nodes and edges.
Yeah, the nodes are the entities, so people, places, concepts, and the edges are the relationships connecting them.
So if I upload, say, a biography of Steve Jobs, it creates a node for Steve Jobs, a node for Apple, and draws a line between them labeled founded.
Precisely. And this is a brilliant way to store information because it allows the AI to perform multi-hop reasoning.
Multi-hop reasoning, meaning it jumps from one thing to another.
Exactly. If you ask a complex question that requires connecting a fact from one document to a completely different fact from another document, the graph structure allows the AI to literally hop across the connections to find the answer. It can just follow the breadcrumbs.
Okay, I'm following the logic. That sounds incredibly efficient, but here is my fundamental issue with the premise.
Okay, let's hear it.
If the AI is building its own highly organized web of knowledge, shouldn't it be perfectly organized? Like, why does it degrade over time? My analogy of the human assistant's filing system getting messy makes total sense for a person, but this is software. We're talking about code here.
Right.
Why does a digital brain systematically fail just from being used?
If we connect this to the bigger picture, we really have to look at how these systems actually function in the real world over months and years. Initially, yes, the knowledge base is pristine. When it's first built, it is a completely static, perfect snapshot. But a static knowledge base is basically useless if you want the AI to learn from you. It doesn't accumulate context from your repeated queries or, iterative workflows. So developers started making these knowledge bases evolvable.
Ah, so they change constantly.
Right. The AI updates the graph constantly as it interacts with you. But the paper points out that this constant editing introduces three main systematic defects: incompleteness, incorrectness, and redundancy.
The degrading brain of the AI. Let's break those three defects down, actually, because I want to visualize what's physically breaking in the graph.
Sure. Let's start with incompleteness. This happens when the AI misses evidence chains or cross-document links. It might say, read a new article and add two related facts to the graph, but it completely forgets to draw the edge connecting them.
Oh, wow. So the information is there, but it's orphaned.
Exactly. So it knows fact A and it knows fact B, but it has absolutely no idea they are related.
That's frustrating. Okay, what about incorrectness?
Incorrectness manifests as low confidence or imprecise assertions. The AI might read a poorly phrased prompt from you, totally misunderstand the context, and just add a node that is flat out wrong.
Garbage in, garbage out.
Yeah, exactly. And finally, redundancy. This is arguably the biggest headache for these systems. It involves ambiguous or coreference resolution issues.
Coreference resolution. Let me guess. Is it the AI not knowing if the word apple in a document means the tech company, the fruit, or like the Beatles record label?
That is a classic example, yes. Or imagine you feed it 10 different news articles about a political event. It might create 3 separate nodes for the president, the commander-in-chief, and the pronoun he, not realizing that all 3 of those nodes refer to the exact same person in that specific context.
Oh, man. And so now the graph has 3 separate messy webs of information instead of one clean one.
Right. And under iterative use, these issues don't just sit there in isolation. They compound over time. Every time the AI uses a redundant node to build a new connection, the tangled web gets worse and worse.
That sounds like a nightmare.
It is. As these messy layers build up, the system's retrieval fidelity basically plummets. The graph becomes so noisy that its performance on downstream tasks degrades entirely. As the AI gets more complex, its memory becomes just as fallible and tangled as human memory if it isn't actively maintained.
It's like a digital hoarder's hard drive. It's saving absolutely everything you give it, but it loses the ability to actually find anything useful because the directory structure is an absolute disaster.
Spot on.
So if the memory is broken, the logical next step is fixing it. But looking at the source material, fixing this seems to be an absolute nightmare for developers.
Right.
Why is repairing a database so incredibly difficult?
Well, it boils down to 2 core challenges. The traditional solution to a degraded AI knowledge base is just to throw the whole thing out and start over.
Just delete it.
Basically. Systems like Autograph R1 approach this by retraining the constructor and recompiling the entire knowledge base from scratch. But doing this post-construction is wildly expensive in terms of computing power.
I can imagine.
Yeah, it is operationally impractical at any kind of scale. You can't just burn down and rebuild the entire library every time a single book gets misplaced.
Right. The server costs alone would be staggering. So ideally, you just want to fix the broken parts. You want to, like, spot treat the problem.
Which brings us to challenge 1, defect localization. These agent-compiled knowledge bases are massive. We are talking about relationally connected graph databases with millions or even billions of connections.
Okay. Wow.
Yeah, you can't just run an exhaustive traversal check, meaning you can't have a program scan every single node and edge across the entire web just to find the errors. It would take forever. You have to somehow find the needle without searching the haystack.
That seems mathematically impossible. How do you find an error without looking for it? And wait, what is the second challenge?
Challenge 2 is policy optimization without golden references.
Golden references.
Yeah, so in machine learning, you typically train an AI by giving it a test and then showing it the answer key. That answer key is called the golden reference. If the AI gets it wrong, it compares its work to the golden reference and adjusts its internal weights to do better next time.
Okay, that makes sense. It learns from the right answer.
Right. But in real-world dynamic knowledge refinement, there is no perfect answer key. We don't have a perfectly mapped, correct sequence of refinement actions to show the AI because the graph is constantly evolving based on what the user asks.
So let me make sure I am visualizing this correctly. We have a massive, tangled web of information that is degrading over time. We don't have a map to navigate it to find the broken parts, and we don't even have an answer key to show the AI what a fixed version is supposed to look like.
That's the situation.
How do you teach an AI to fix a mistake when you can't explicitly tell it what the perfect fix looks like?
It is a fascinating computer science puzzle, honestly. You have to teach it intuition, essentially. And that impossible puzzle is exactly what DeepRefine is designed to solve.
Here's where it gets really interesting. Because DeepRefine doesn't try to rebuild the whole database. It uses a 3-step reasoning process that acts like a surgical microprocedure.
Exactly.
Instead of a full-body transplant, recompiling everything, it just operates on the specific problem area. And the genius part is that it uses the user's own questions to trigger the healing process. Step 1 is the answerability judgment loop. I'm going to compare this to a doctor diagnosing a patient. This loop is the initial physical exam.
The doctor analogy works perfectly here.
Yeah.
During this multi-turn interaction, DeepRefine essentially waits for you to ask a question. Let's say you ask about a complex historical event. DeepRefine takes your query and does a dense retrieval of the top n related triples in the graph.
Just to clarify, a triple is just two nodes and the edge connecting them, right? Like
Yeah.
Steve Jobs founded Apple.
Yes, exactly. It pulls the most relevant triples and creates a zero-hop subgraph. It looks at this very small, localized neighborhood of information and asks itself, can I answer the user's query with just this?
And if it can.
If it can, it stops. The patient is healthy. But if it can't answer it, it expands the subgraph hop by hop. It pulls in the candidate triples connected to that first neighborhood, prunes them down to the most relevant pieces, and checks again.
It's systematically widening the search radius until it either finds the answer or hits a dead end. And if it hits a dead end, that brings us to step 2, which is error abduction. This is the deductive reasoning phase of our medical diagnosis. But how does an AI actually do deductive reasoning? It's not a human detective.
Well, it uses something called chain of thought prompting. DeepRefine looks at the entire interaction history, the expanding search radius we just talked about, and abductively reasons why the query couldn't be answered.
So it's looking back at its own steps.
Yes. It generates an internal monologue to act as a diagnostic detective. It analyzes the retrieved subgraph from those 3 perspectives we mentioned earlier.
Yeah.
Incompleteness, errors, and redundancy.
So it's basically talking to itself saying, I see the node for the company and I see the node for the founder, but there is no edge connecting them. That's why I can't answer the prompt.
Exactly.
Or like, I see 2 conflicting dates of birth here. This node says 1980, this one says 1982. That's a redundancy error.
Yes, that's exactly what it's doing. And notice what just happened there. Because it's only looking at the interaction history from that specific query, it completely bypasses challenge 1.
Oh. Because it doesn't need to traverse the whole database.
Right. It doesn't need to search the massive database to find errors. It only searches the localized neighborhood where your specific query just failed. The user's question naturally localized the defect, which sets up step 3, refinement actions generation, the microsurgery itself.
So we found the broken part of the graph. We know why it's broken. Now it actually has to write the code to fix it.
Based on the abductive reasoning it just did, DeepRefine generates targeted executable actions to edit the full knowledge base directly. It uses 3 predefined types of operators.
And those are?
Well, insert a edge to fix incompleteness, delete edge to remove incorrect relations, and replace node to resolve ambiguity.
I read the paper closely on this part, and these operators are actually quite complex under the hood. It's not just, hitting backspace.
Oh no, not at all.
If it decides it needs to execute a replace node action, say, merging the president and commander-in-chief into one node, it has to integrate several distinct API steps. It has to delete the original nodes, delete all the edges connected to them, insert the new unified node, and then draw all the new edges back to the rest of the graph.
It's a whole sequence.
Yeah. It's autonomously writing code to surgically alter its own database in real time.
It is highly sophisticated self-correction.
But this brings me back to the biggest question. I understand what DeepRefine is doing mechanically, but how did the researchers actually train it to do this? We established in Challenge 2 that there is no golden reference answer key.
Right, the missing answer key.
Yeah, if there's no answer key to show the AI what a perfectly fixed graph looks like, how does it learn whether its surgery was successful or not?
This is where we get into the actual training architecture. The model is trained end-to-end via reinforcement learning. They use an algorithm called GRPO, which stands for Group Relative Policy Optimization.
Okay.
Now, usually in machine learning, they use something called a KL divergence term. Think of KL divergence like a mathematical leash. It keeps the AI from completely abandoning its original training while it learns a new task. It prevents the model from acting wildly out of character.
A leash makes sense. You want it to learn, but you don't want it to, forget how to speak English in the process.
Precisely.
Mm-hmm.
But calculating that leash at every single step takes up a massive amount of computing memory, especially on large language models. So interestingly, the researchers simplified the training procedure by dropping the KL divergence term entirely, and instead, they baked that constraint directly into the reward penalty.
Oh, wow. That's clever.
Yeah, it significantly lowers computational overhead. But the real breakthrough here is the reward system they created to replace the missing answer key. It's called the Gain Beyond Draft, or GBD reward.
Okay, let's unpack the GBD reward. How are we scoring the AI if we don't have an answer key? Are we just judging it based on whether it gets the final question right?
That's the core of it, yeah. It measures downstream utility.
Right.
It doesn't judge the intricate structure of the graph directly. It just judges the results. It compares the RA generation accuracy of the draft knowledge base the messy graph before the surgery, against the refined knowledge base, the graph after the surgery.
Okay.
They set up a point system based on 4 possible transition states.
Let me guess how this works conceptually. If it starts with a broken graph, performs surgery, and now it can answer the user's question, that's a win.
Spot on. If the draft couldn't answer the query, but the refined version can, that's a successful correction. A state change from 0 to a 1 that gets the highest reward plus 1.0 points.
Nice.
Now, what if the draft was already correct, the AI tweaks it, and the refined version is still correct? A 1 to a 1 state.
I would assume that's good, but maybe not as good as fixing a broken one.
It's a correct preservation. It gets plus 0.2 points, reinforcing confidence. Now, if the draft couldn't answer it, and the refined version still can't, the 0 to a 0, that's a failed correction.
Right.
Gets a neutral 0.0 points.
Sure.
But the final state is the danger zone. If the draft was perfectly correct and the AI surgery breaks it so it can no longer answer the query, a 1 to a 0 that is an erroneous alteration, it gets a penalty of minus 0.3 points.
Okay, wait. I have to push back on this math here.
Sure, go ahead.
If fixing a mistake gets the AI a plus 1.0 reward, why does breaking a perfectly correct answer only penalize it minus 0.3? Shouldn't the punishment be much worse? If you perform unnecessary surgery and, kill the patient, shouldn't that be a massive penalty, like a minus 1.0?
It's a really great question, and it speaks to the psychology of reinforcement learning, actually. When you train an AI, you have to balance 2 competing drives.
Yeah.
Exploitation, doing what you know already works, and exploration, trying completely new things to find better solutions. If the penalty for making a mistake is too harsh, say a full minus 1.0, the model becomes terrified. It becomes paralyzed. It realizes that touching the graph is incredibly risky, so it plays it entirely safe and just stops trying new refinement actions altogether.
Oh, I see. If the punishment is too severe, it decides that the safest way to avoid losing points is to just never do surgery.
Exactly. The minus 0.3 penalty is carefully calibrated. It's just enough to discourage over-editing and stop the AI from randomly deleting healthy nodes. But it's forgiving enough that the AI is still willing to take calculated risks to learn how to fix complex problems.
Okay, so they built this incredibly elegant 3-step surgical system, and they trained it using this clever GBD reward system so it learns without an answer key. The theory is brilliant, but, AI papers are famous for working in theory and failing in practice.
Sure.
Did they actually test this surgical approach against a traditional wipe and rebuild?
They did, and the results are actually pretty definitive. They tested DeepRefine using a couple of different backbone models, and they ran it against datasets that are specifically designed to trip up AI.
Like trick questions.
Yeah, these aren't simple trivia questions. These are datasets filled with massive, tangled webs of multi-hop questions designed to confuse language models with distracting information and complex coreferences.
Okay, so a real stress test.
Exactly. First of all, the DeepRefine approach proved vastly more efficient in terms of time. In their testing, a full reconstruction of the database using the traditional autograph R1 method took roughly 6,782 seconds. DeepRefine took only 3,201 seconds.
Less than half the time. That's a massive operational savings. And the paper mentions something called a greedy maximum coverage procedure to boost that efficiency even further. I know what that means conceptually, but how does an AI act greedily here?
Well, it's a mathematical optimization strategy. Greedy means that at each step, the algorithm chooses the action that offers the biggest immediate payoff. Before DeepRefine even starts its surgery, it looks at a batch of failed user queries.
Okay.
It calculates which single query is connected to the largest overlapping chunk of the broken graph. It targets that neighborhood first.
Oh, that makes sense.
Yeah. By fixing the most interconnected errors right out of the gate, it prevents itself from redundantly analyzing and fixing the exact same region of the graph twice. It fixes a dense neighborhood once, gets maximum coverage, and moves on.
It's finding the absolute biggest bang for its buck before it does any work. That's smart. But speed is only half the battle, right? Is it actually more accurate than rebuilding? You would think starting fresh with a brand new graph would always yield cleaner results.
You would think so,
Yeah.
but DeepRefine often outperformed full reconstruction in downstream performance. They measured this using something called a token-level F1 score.
F1 score.
Think of an F1 score as a very strict grading scale for accuracy, measured out of 100. On one of the most complex datasets, the full reconstruction method scored a 26.21. DeepRefine scored a 28.27.
Okay, for anyone listening, going from a 26 to a 28 might not sound like a huge jump out of 100. But in the world of rigorous AI benchmarks, Moving the needle 2 whole points on a complex multi-hop reasoning test is a massive leap. How does a partial fix actually beat a total rebuild?
Because regenerating a massive knowledge base from scratch isn't a flawless process. When you force the AI to re-ingest and recompile every single document in its library, you often introduce entirely new noise and new errors into regions that were previously fine.
Oh, right?
It's like rewriting an entire encyclopedia from memory just to fix one typo on page 50. You're bound to introduce new typos somewhere else in the process. DeepRefine surgical edits only target the broken logic. It leaves the healthy tissue, the structurally sound parts of the graph, completely alone.
That makes total sense. Why risk breaking the good stuff? If you've ever felt completely overwhelmed trying to keep your personal notes organized, or watched a company database turn into an unsearchable swamp of duplicate files and broken links, DeepRefine represents a pretty incredible future.
It really does.
We're looking at a paradigm where your digital tools autonomously audit themselves. As you ask them questions, they use your failed questions to diagnose their own structural flaws, and they quietly heal their own knowledge structures in the background. It is the ultimate self-cleaning oven for information.
It really is a paradigm shift for how we maintain AI systems long term. But, looking at the architecture of the reward system we discussed, this actually raises an important question.
Oh, what's that?
We talked about the GBD reward states. A successful correction gets a plus 1.0, an error gets a minus zero point 0.3. But a failed correction, when the draft was broken, the model tried to fix it, and it remained broken, it gets a neutral zero point 0 reward.
Right. And you said the researchers did this so the model wouldn't get destabilized and terrified by incredibly hard multi-hop reasoning questions that it just couldn't figure out.
Exactly. You don't want to punish the AI for failing to solve a puzzle that is fundamentally too difficult for its current reasoning capabilities. But consider the long-term implication of that.
Okay, I'm listening.
If an AI is given zero punishment for constantly failing to fix an incredibly complex, deeply buried flaw in its knowledge base.
Wait, does it just learn to ignore it?
Right. Does the system eventually learn to simply ignore its hardest problems? If there is no negative feedback for that 0 to 0 state, could this neutral state create permanent, invisible blind spots in the AI's worldview? Blind spots that it fundamentally lacks the incentive to cure.
Wow. That is a fascinating thought to mull over. If your digital assistant realizes they never get yelled at for ignoring the messiest drawer in the filing cabinet, well, they're never going to clean that drawer. And eventually, whatever truth is buried in there is just lost forever.
Something to definitely keep in mind as these systems become the invisible foundation of our external memory.
Absolutely. Thank you for joining us on this deep dive. Until next time.